All right, let's look at another example. While I'm thinking about this, I'm going to go to my calculator. Let's clear this calculator's memory so we're ready for our new analysis. So I'm going to go to Second, Memory, Reset, All RAM, All Memory. And yes, I do want to reset. There we go. We're in a good space here to start a new problem. Suppose I travel by car for 1 hour and 15 minutes to an IMAX theater that's 100 miles from my home. I stay at the theater for 3 hours before returning home, and the return trip takes 2 hours. I'm going to assume a constant rate of change on each leg of my trip. My distance d from home in miles is a function of the elapsed time t in hours. I mean, that just physically makes sense. I can only be in one place at a time, so for every time, there will be one and only one distance that there will be one and only one distance from home. And I want to write a formula for that model. D is a function of t, d of t. So, what's going on here? This is a good example. Like the last example, a sketch is extremely helpful here. First of all, our D is in miles from home. Home will be, when I'm at home, I'm 0 miles from home. So D is equal to 0 when I'm at home. And then I'm moving away from home and then coming back to home. So D will be positive, a positive distance from home. The elapsed time is our independent variable, t, and so t is equal to 0 at the beginning of this trip that I take when I'm at home. So I'm going to start drawing a graph. Here is my t-axis is the horizontal axis, and the vertical axis is the d-axis. This is in miles. The origin that's where I start. That's going to be a point on my model, the point 0, 0. T is in hours. That's the way we wanted to set up our independent variable. T is in hours. So I travel by car for 1 hour and 15 minutes to an IMAX theater. In hours, 1 hour and 15 minutes is 1 plus 15 divided by 60, which is 1.25 hours. So at 1.25 hours into my trip, I'm 100 miles from home. Let's put that on our graph. I'm going to say, let's see, what kind of scale do I need on my t-axis? Notice that, so I'm at 1.25 hours here. I stay at the theater for 3 hours. That would take me to 4.25. And then the return trip takes 2 hours, which the whole trip is going to take me 6.25 hours. So I'm going to draw a little scale here on the t-axis. I'll say this is 1 hour, 2, 3, 4, 5, 6. So roughly like that. So now, at 1.25 hours, which is about here, I'm at 100. I'll put it right there. That's good enough. So there's that point when I get to the theater. We're assuming a constant rate of change for all legs of the journey, so I'm assuming that my model is linear between those 2 points. So that's the first part of my model. Now what happens? I stay at the theater for 3 hours. So for the next 3 hours, from 1.25 to 3 hours later, which would be 4.25, so here's 4.25 right about here. All of this time, that's at 4.25, I'm right there, and that's when I start heading home. were there the whole time, so our linear chunk is a horizontal line segment right there. There I am at the theater for that 3-hour period of time. And then, after that 3-hour period, I return home and the return trip takes 2 hours. So the return trip takes 2 hours, so from 4.25 to 6.25, right about here, that's when I arrive home. And so a constant rate of change there. There's our model. This is going to help immeasurably. This is the point 1.250, 1.25, 100. This is the point 4.25, 100. And this is the point 6.25, 0. I've got enough information to look, we want to model d of t. So we want a model that captures this whole model, this whole graph. And so I'm going to label my line segments 1, 2, and 3 and come up with some subformulas. What's the formula for that first increasing line segment? Well, the slope of that line, A, is delta D over delta T, which is 100 minus 0 on the D-axis divided by 1.25 minus 0 on the T-axis, which is equal to 100 divided by 1.25, or 80. 80, notice the units, miles for D, per hour for T, miles per hour. I'm assuming a constant rate of change here. I had to travel 80 miles per hour on average to get between those 2 points. Clearly I was going fast. If I traveled on average at 80 miles per hour, I must have been really rushing to get to that IMAX theater that's significantly far from my home. So that's the equation for that's the slope for part 1. Now, for part 1, I have a choice here. I can use point slope form or I can use slope intercept form. I know the d-intercept. The d-intercept is 0 right there. When the input is 0, the output is 0. So I hit the d-axis at d equals 0. And so that means that I know the intercept, so I can just write the subformula here is on line segment 1, d is equal to 80 times t plus 0, which is just 80t. So that's my first line segment. Line segment 2 is what? Well, line segment 2 has a slope of 0. It's a horizontal line, and any horizontal line is just d equals 0 times t, 0, plus the d-intercept, which is 100. See how that horizontal line segment, if we bring it back all the way back to the d-axis, that's at d is equal to 100. So d is always 100 between 1.25 and 4.25. And then line segment 3. I'm kind of running low on space here, but here I'll write it right up here. For line segment 3, here the slope, A, is equal to, so this is again delta D over delta T, which is 0 minus 100 divided by the 6.25 minus 4.25. A little sloppy here, but we get the idea. And this is equal to, in the numerator, negative 100 divided by the 6.25 minus 4.25 is 2, and so that's negative 50 miles per hour. And so what does that equation look like? That equation I think I'm gonna do this. I'm gonna write it down here. So for 3, we've got D is equal to, and then I'll write it as, I'm going to use, here I don't have the d-intercept for this line segment, right? This line segment continues on back that way, so the d-intercept is somewhere way above 100. I don't need that because I've got points on the line. I can use either one of these points. I'll write it with that first point on the line segment. So d is equal to the slope, negative 50, times t minus the known input, 4.25, and then plus the output corresponding to that input, plus 100. Now, just in words here, I could have written negative 50 times the quantity t minus 6.25 plus 0. I could have used the second point right here along with the slope, and algebraically it would be exactly the same thing. And so now we've got subformulas for all of the segments. We know on what segments, for what t-values those segments hold. For the first subformula, we're going to go from 0 on the t-axis to 1.25, and then from 1.25 to 4.25 on the t-axis, we'll use the second subformula, and then from 4.25 to 6.25, we'll use the third subformula. So all we need to do now is write that model in our standard way. This is all the work we just did. The only thing that I did here is after writing this, I happen to note that this is equivalent to negative 50 times t plus 312.5. If you take that negative 50, multiply it by negative 4.25, and then add 100, you get 312.5. You could also use linear regression on the 2 points to directly get that formula in slope-intercept form. So now let's write the formula in the standard way. D of t equals, and then next to the curly brace, thinking of t moving from left to right, we write the formulas in that ascending order. 80t for the first line segment, 100 for the second line segment, and negative 50t plus 312.5 for the third line segment. Any algebraic form for any of those, any equivalent algebraic form for any of those line segments would be fine. So I didn't have to write slope-intercept form here. I could have stuck with the point-slope form. I'm going to go ahead and put that model into my calculator. By putting each of those 3 subformulas into y1, y2, and y3 respectively. So 80t for y1, 100 for y2, and negative 50t plus 312.5 for y3. I just checked my work there. And now I already know the viewing window that will work for me, or at least close enough. On the t-axis, I can put the model domain, which is 0 to 6.25. That's my entire trip in hours. For the output values, remember, ZoomFit doesn't always work great here with when you have more than one formula. I already know a window or one window that will work just fine. I can go with a minimum d value of 0, that's home, and a maximum d value. I could, if I put 100 here, then that horizontal line would be right on the top of the screen. I'm going to put a little higher than that, like how about 110, just so that there's a little breathing room up top. And hit graph. And there I can see my first line segment. So my model goes from the origin to that intersection point, and then across, and then down from that second intersection point. Anything above there we're just going to ignore, and anything before those intersection points and after those intersection points I'm going to ignore. So this kind of lower trapezoid is the model, which corresponds to our sketch.